Okay, so welcome back to another episode of Pollys Introduction to Computer Networks. And so we will have 4 quizzes doing, but the due date is a little bit special this week. The due date will be Sunday, November 27th, because you guys will go out and vote on Saturday, all right? Oh yeah, Victor, welcoming. I know that the international students don't get to vote. Anna. Good afternoon. Yeah, so 4 quizzes doing, but on Sunday. All right, great. And the topics for today. Guys, congratulations. We are moving on to finally the network layer. So the network layer is actually composed of 2 chapters. And today we'll start from overviewing chapter 4. Okay, and here's the video. Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer: forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, okay, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now, to be exact, okay, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram, and sometimes also called the IP datagram. Okay, so transport layer, TCP layer; network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. Okay, so at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, okay, datagrams, will go on to the network and travel from router to router. And each of the router will examine something special, okay, in the packet header, in the IP datagram header, okay, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, okay, so this is the receiving host, yeah, the network layer is going to look at the datagram, remove the packet header, and pass the segment, okay, up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in NMA, so packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up, okay, to the higher layer. All right, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing 2 major functionalities. As you observed earlier, yes, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully, it gets to the next router that is appropriate so we don't take too much time to pass the packets until it reaches the receiving host. The other is this, okay, this is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines, okay, a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end end-to-end paths to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to canteen. Yeah, I know the weather is getting warm. It would be really nice if we're in canteen. Okay. Well, the thing you need to do first is this, routing. You pre-compute or you Google, okay, and come up with a plan, okay, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take a high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus, or do we all rent a car or rent a number of these bikes so that we ride along all the way to canteen? Okay, so the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to canteen. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function. All right, so now if you recall, in transport layer, we say that we established a logical channel between the end hosts, right? In network layer, you will see that we realize that logical channel, and you will see it's physically lots of segments between the routers connecting the end host to another end host. Now, you get also a rough sense that there are actually two very important functions, forwarding and routing. And you kind of do routing first. There's some intelligence that needs to be done. And then so that when you are traveling in real time, you can quickly maneuver through the routes and get to the destination. All right. Next video is to emphasize a little bit more these two functions, forwarding and routing. And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay? And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay? And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port, and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, implementing the intelligence. It is to determine, how would the packets be able to travel end-to-end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the SDN approach. Okay? The traditional one is the distributed approach. And the modern one, the SDN one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the SDN, we actually ask a couple very powerful machines, a couple very powerful SDN servers that are actually sitting far away from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. So the tables are actually computed on the routers locally in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. And it's very simple, very fast.
Okay, all that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. Okay, so this is called the fast output interface lookup. Okay, once we get a match, we get also the outgoing interface. Okay, let me illustrate. So these are the routers. Okay, and inside the router, okay, you see this is the entire operating system stack. Okay, there's this thing called the forwarding table, and each router will have one of these. Okay, when there's a packet coming in like this, it's going to look into a packet header field, okay, and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. Okay, so output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. Okay, so this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, okay, higher up in the operating system stack. To be more exact, okay, and let's talk about the traditional approach first, where the computation is distributed. Okay, so the routing algorithm is going to be running on each of these routers, okay, and up here. Okay, the routing algorithm here, 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 and here. Okay, so each and every router, okay, is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages, okay, between these routing algorithms distributed on the routers. Okay, and this is the control plane. Okay. As a result of the computation and exchange, okay, they find out what should be the forwarding table, okay, for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the SDN approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here, because the computation is all where? Up here, okay, a couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is going to provide input to the remote controller. This is the big process, implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers.
All right, so you see, in a router, you have this control plane doing the intelligent, right, routing function. And then there's this data plane doing the very, very fast, high-speed data forwarding. Now, this is an internet's model. Okay, so traditionally, there are actually two kinds of models to do network layer, okay, how we pass data around. So network layer is also nicknamed the layer 3. So next video, let's check out the different models of doing L3.
Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out, and the data is just going to arrive. But unfortunately, yeah, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity, okay, of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. Okay? So the service model we'll be talking about next is to talk about how we implement. Okay? What kind of channel we're providing here. Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. Okay, so you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay? And this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. Okay. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, okay, ATM is actually competing with the internet. I think towards late 90s, okay, still before the turn of 21st century, ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old, okay, but these are examples of connection-oriented network layer service. Okay. Now, to establish such a connection will involve routers, okay, and the involvement is actually quite deep. It's complicated enough. It's the third important function, okay, in these systems, on top of routing and forwarding. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN ACK, and then ACK for the SYN ACK. Hey, that's the establishing connection, right? It sounded very much like these, ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. All right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers.
All right, so again, complexity at the edge. So internet is actually taking the very simple model, the best effort service model. We're not quite yet done with the service model because we won't be talking about this other type, the connection-oriented L3 model. So let's just go over one more video that will take you into what these connection-oriented model type of network do. Okay, so it's definitely not how we do it in internet. Okay, but let's check out what the alternatives are.
Yeah, those are the major camps. But within each camp, you can probably define finer service models so that you provide different levels of service. So, for example, okay, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, or we restrict the time differences in between these packets when they arrive. So again, the service models, they can be finer or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time in ATM's case, and continue to be used today on the internet as well. So the internet service is, the best effort. So essentially, it's not guaranteeing anything, no guarantee at all, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer, between the TCP sender and receiver. Now, ATM, quite sophisticated, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. So this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. Okay, so you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now these two, however, okay, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. Okay. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee. And in this case, no longer a congestion signal going back to the data source. So you see, again, network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, there's just one model we talk about, the best ever. Okay.
All right, so that's L3, the alternative service model. And we do have two questions from the students. First is from Wei Shan asking, how does router acquire the graph of the whole network so you can do the route computation? It's a very good question. I think many of you are probably asking the same thing. You know what? We do have one routing algorithm running on the internet that does require a graph before you can start doing the route computation. And we'll talk about how the graph is formed, calculated, collected at the time. There's actually, Wei San, another routing mechanism that does not require the graph of the whole network, and yet you can still compute routes. Okay, so yeah, I know. Stay tuned. When we start chapter 5, you'll hear about these different flavors of routing algorithms and how they gather and or figure out what is the best route very differently. And Vincent was asking, routing algorithm continue. Oh, okay. This is yet another very good question. It's also in chapter 5. But what I can say now is that route computation versus data forwarding. Data forwarding, packets will come. Whenever there's a packet coming, you need to do it right now. Otherwise, you generate delay. That is also called the processing delay in the nodal delay. Recall chapter 1, right? How do we calculate delay? There are 4 components. And we said that the processing delay is often neglected because that forwarding thing is going really, really fast and should be going really, really fast. So forwarding part, the time scale of its running, time granularity of its going is nanosecond. But route computation, you see that the routers on the internet, they are more or less stable and well connected. The chance of them failing and then coming back up, you see that the frequency is not high. So that route computation, it runs once for a while. Okay? It can be periodic. It can also be triggered by events. So it's interesting. It's continuously running, but it's not necessarily a fixed periodic process. And Yo Xiang was asking, why is the word plane using the term data plane, control plane? Yeah, so plane meant actually a flat space, or sometimes you call, a higher plane a space, and then a lower another space. So they kind of, the authors of the textbook or the network engineers would like to kind of separate discussions of routing functionality versus forwarding functionality. So the routing, we just say this is control plane problem. If it's a forwarding problem, we just say this is a data plane problem. Okay. Yeah, it's a choice of terminology. We could say a control space problem or data space problem. Okay, I hope that addressed your question. All right, and we move on. So that was the overview. Next, let's take a closer look into what's in a router. Okay, so let's start from the architecture.
Now let's take a look into the inside of a router. This is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. Okay? And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay? By output ports, input ports, I actually meant that these network interface cards, okay, that we use to connect to the routers that are passing data in, passing packets in, as well as connecting to routers, okay, that we pass the packets out. Okay. Now, you see then, yeah, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, yeah, the computation, the switching there is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay? For example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, the one most important functionality for the router to do is forwarding. Now, it also does route computation here. Okay. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface here. Let's zooming a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay, so what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay? So the forwarding of packets coming into each of these input ports is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet, okay? And it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. So the goal here for the incoming network interface is so that it can complete the input port processing, the lookup forwarding at the line speed. Okay? Meaning, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. Okay? If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we'll end up having this. Okay? Packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queuing delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. Okay? So it's a lot more general. But you can also see that provided the same lookup processor, okay, this is going to be a bit faster and this is going to be a bit slower. So in order to keep up the speed, okay, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, okay, these SDN routers we'll need a faster lookup processor here. So this one here, SDN routers, more expensive, while this one here, usually more affordable.
All right, and the most important topic today. Yeah, so on the internet, at least for the traditional forwarding, we do this. Okay, the router at the data plane is repeatedly doing this longest prefix match. And this next video explains how it works.
So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Okay? Destination-based forwarding. Okay? As you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. Okay? So if the destination address says this, 11001000, matching this guy here, then we take this output port, okay, output link interface. If it matches, for example, this IP address, okay, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this is this particular destination's output interface being 0. So in fact, okay, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface? For each of these IP addresses, what is the output link interface? But the thing is this. Okay, how many possible destinations there can be? Well, the IP address is this big. Okay, the IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. Okay, and each entry might require, you see, 4 bits. 4 8 bits. That means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that would be 5 gigabyte at least, just to keep the forwarding table. Okay, so the input port network card there, okay, it's gonna require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually, expand the IP address space. So this is a 32 bits IP address. This is IP version 4. Later on, you'll see. Okay, there's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry, is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing table lookup is to do matching, but we are only matching to the longest prefix. Okay. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay. This time we don't have 1 entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. Okay. So that is also saying that as long as the destination address, the first few bytes match this pattern, okay, the rest of the IP address can be general, free. Okay. Now, as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that, okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Right. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Okay, now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. All right. So let's exercise a little bit. Now, if we get a packet, the destination address is this. what should be the output interface? Let's see, the first 8 bits match, great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, yeah, the first 20 bits are all the same. So these two destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these two not matching. Therefore, this packet goes to interface 0. Now, the second destination here. Oh, 21st bit is 1. So it should be either one of these. Now, 0, 0, 0. Well, it actually matches more the second entry. Therefore, the outgoing interface for the second destination address being 1. And that takes us to a double quiz time.
All right. Yeah, Agent asked a very good question, Zijun. Yeah, so you see that those entries going to interface 1 and interface 2 overlap. That is exactly to demonstrate what it means by doing longest prefix match. Because by doing longest prefix match, we don't need to have 7 more entries to separate them from the 11100, something something and then 111 part. We don't have to have 7 other entries all going to interface 1. Okay, so this way, doing longest prefix match, we don't need to have the prefix strictly non-overlapping, and it will still work. So you have fewer entries in the table, and it's faster to do lookup. Okay, so let's start with the quiz. Okay, quiz 30 is trying to make you exercise the longest prefix match. So let's see. We have a forwarding table that looks like what we have here on the top, right? Again, 3 entries. Okay, and okay, sorry, Agent. I actually meant that we don't need to have 3 other entries all going to interface 1. Okay, because there are only 2 more bits, okay, that are not matching. All right. Oh wait. Okay, this is very fast. Okay, good. So then I probably don't have to explain because you guys already see that Polly did a couple examples in the video, right? So let's see. Team 14. First entry goes to interface 3, otherwise, right? Second, interface 2. Let's see. Vincent also 3213. Agent 3113. Let's see. Q2. Okay, so I think only the third octet. Okay, 0001100 will be the value of Q2. So does that match? It does match the second entry and the third entry, Agent, isn't it? But you know what? We need to do longest match. So among these two, we actually go with the longer match, which is the third entry that goes to interface 2. Okay, so hope that you get the idea, Agent. All right, so I see that team 13 and team 14. So essentially, guys, what you do is, for example, Q1. I think it's the third octet is really where you want to do the matching here. Okay, 0011. 0011. Actually, you match to the third bit of the third octet, and you see none of these entries, top, second, and the third matches. Therefore, it must be otherwise. Okay, therefore, we get interface 3. For Q2, the third octet, 0001. Oh, okay, all 3 entries at the top match. Okay, 1000. The first entry doesn't match, obviously. Second entry match. Third entry also match. But between the second and the third one, that match is longer in prefix. And therefore, this type of match that we select, the longest prefix match, is called the longest prefix match. Okay, so therefore, second there, matches to interface 2. Okay, very good. I see that you guys are getting it. Now, the next quiz. Okay, so there's another exercise, okay, related to the longest prefix match. This is how you generate. Time for vision test. Oh, sorry about that. Okay. Yeah. Okay, Leon. Guys, all the best. I think as long as you try the best you can, just take things easy. Okay. Generating the table. So you see that the first entry there, what I'm showing are exactly all the IP addresses there. And this is without doing the longest prefix match. But if you want to do the longest prefix match, how should you change this table so that you're only showing the prefix? So IP address from, let's start from the third octet. 1000, and for the fourth octet, 00. Okay, and this IP address starting from here all the way to, okay, the third octet is the same, and the fourth octet, it needs to count all the way to 00, and the rest being 1. So how are you going to represent this set of IP addresses using a prefix? Second set, I think, second set, you want to start from the third octet, right? Because you start seeing differences there. And for the third entry, I think it's at the end of the third octet. Okay, so let me go to that quiz. Yeah, I see that some of you already typed the solution up. That is okay. Yeah, because you can see it also on the stream. Let's see. Did Vincent get it right? Yeah, you're right. So, right, it matches all the way to the first 2 bits. And then the last 6 bits in the last octet are all free. Can be anything. So you match to the first 2 bits. And for the second entry, you match to the first 3 bits in the second octet. So you have 110. So let me show Team 13 solution here. Okay. So first entry matching to the first 2 bits, the last octet. Second entry matching to the second octet, but the first 3 bits. And the last entry, matching all 7 bits in the third octet, because the IP address begin to differ, right, from the last bit of third octet. And then otherwise, 3, exactly. Okay, Zijun, yeah, very well formatted. Okay, it's a lot easy to see, a lot cleaner to see. Okay, I see Team 14. I think Team 14, yeah, Jade. You probably type up more, but edited it out. Okay, so at least Team 1 and Team 13 are correct. All right. Good. And you know what, guys? That's actually all for today. So, hey, I know that many of you are taking the vision class. So, the rest of you, keep on working on the quizzes, quiz 30 and 31. And if you have questions, feel free to type it up on the chat. Otherwise, you're free to go. All right? Bye, go, run. Yeah, you want to be there early so that you can, settle your emotion a little bit and set your nerves. Go, Vincent. Go, Leon. Go, Minnie. Sorry. Yeah, bye. See you tomorrow. Okay, this is another way to show format, I think. Yeah, you put the interface on the left, right? It's okay. Very good. Very good. Simon, that's all right. And Kevin. Yeah, so it's a bunch of numbers. It's a little bit hard to line them up very well. Okay, bye. Waiting for the music. Okay, here it is. Now, I know some of you are probably sitting in the background and not really listening. Yeah, so the music is the cue. Sorry.